Linear Algebra II, Tutorial 5, Euclidean Spaces. Problem 1. Let E be an Euclidean space and x and y two elements in E. Show that the scalar product between x and y can be computed as 1/2 of the following expression: the length of x plus y squared minus the length of x squared minus the length of y squared. And the second part of the problem, determine the scalar product between x and y in the case when the length of x plus y is 6, the length of x is 4, and the length of y is 2. Solution. We can do the following computation. The length of x plus y squared, by definition, is the scalar product between x plus y and itself. Now we can use the bilinearity of the scalar product to rewrite this expression in the following way. So the scalar product between x plus y and x plus y is equal to the scalar product between x and x plus the scalar product between x and y plus the scalar product between y and x plus the scalar product between y and y. Here we can see that the scalar product between x and x, this summand, is exactly the length of x squared. This summand, the scalar product between y and y, is the length of y squared. And these two summands are equal because the scalar product is symmetric. And we see that the scalar product between x and y is equal to 1/2. From the left-hand side, we have the length of x plus y squared. And from the right-hand side, we have minus the length of x squared minus the length of y squared. So this proves the first part of the problem. Now for the second part of the problem, we can explicitly compute the scalar product between x and y by plugging in the numbers into our expression. So the scalar product between x and y is equal to 1/2 of the length of x plus y squared, this is 6 to the power 2, minus the length of x squared minus 4 to the power 2, and minus the length of y squared minus 2 to the power 2. So 6 to the power 2 is 36, minus 16 minus 4, we get 16 divided by 2, and this is equal to 8. And this completes problem 1. Problem 2. Let E be an Euclidean space and x, y, and z three elements in E. Assume that the length of x minus y is greater than or equal to 2, but less than or equal to 3. Assume also that the length of y minus z is less than or equal to 1. Show that the length of x minus z is greater than or equal to 1, but less than or equal to 4. Solution. In order to estimate the lengths, the best way to do is to try to use a triangle inequality. So to estimate the length of x minus z, we can write x minus z as x minus y plus y minus z. So we added and subtracted y, so we didn't really change the expression. But now we have the sum of two elements, so we can use a triangle inequality to say that this expression is less than or equal to the length of x minus y plus the length of y minus z. The length of x minus y is bounded by 3 from above, so this expression is less than or equal to 3 plus, and then the length of y minus z is bounded by 1 from above. So 3 plus 1 is 4, which is exactly the right inequality in our formulation. So now we need to prove the left inequality. So similarly, using the triangle inequality, we can write that x minus y is x minus z plus z minus y. So the length of x minus y, it is of course equal to the length of x minus z plus the z minus y. So by the triangle inequality, this is less than or equal to the length of x minus z plus the length of z minus y. So therefore, now if we move the length of z minus y to the left-hand side, we get that the length of x minus z is greater than or equal to the difference between the length of x minus y and the length of y minus z. But we know that the length of x minus y is at least 2, while the length of y minus z is at most 1. So therefore their difference is at least 1. And this completes problem number 2. Problem 3. Let E be an Euclidean space and M a subset of E. Let M in bracket be the linear span of M. Show that the orthogonal complement to the linear span of M coincides with the set of all vectors W in E which are orthogonal to all elements in M. Solution. Recall that the orthogonal complement to a subspace, so the linear span of M is a subspace. So the orthogonal complement to the subspace is defined as a collection of all elements in E which are orthogonal to all elements in our subspace. So we see that to define the orthogonal complement of the subspace, we use more conditions than in the right-hand side of our formulation. The right-hand side of our formulation says that the vectors should be orthogonal to all elements in M, while the orthogonal complement of the subspace asks for these vectors to be orthogonal to all elements in the linear span of M. So here we have more conditions. Therefore, naturally, the orthogonal complement to the linear span of M is a subset of the right-hand side of our formulation, simply because this right-hand side has less conditions. So in order to prove that they coincide, we need to prove the inclusion in the opposite direction. Now let us take any element v in the linear span of M. So by definition, we can write this element as a linear combination of elements in M with some real coefficients. And linear span consists of finite linear combinations, so only finitely many of those coefficients are non-zero. Now let us take any element from the right-hand side of our formulation. And let us try to compute the scalar product between this element W and our element V from the linear span of M. So since we know that V can be written in the form of such a linear combination, we can plug in this form instead of V in our expression for the scalar product. And now we can use the linearity of the scalar product with respect to the second argument to move the sum and the scalars out of the scalar product. So we get the sum over all m in M, the coefficient alpha m times the scalar product between W and M. But since W was from the right-hand side set in our formulation, by definition, it is orthogonal to all elements in M, so all these scalar products are 0. So we have a sum of alpha m times 0, which is 0. This shows that our W is orthogonal to any element in the linear span of M. In other words, this implies that the right-hand side in our formulation is a subset of the orthogonal complement to the linear span of M. And combining these two inclusions, we get the statement of the problem. So this completes problem 3. Problem 4. Determine the coordinates of the vector W, which is 1, 1, 1, with respect to the following orthonormal basis in E3. So this orthonormal basis consists of 3 vectors. The vector v1, which is 1 divided by the root of 2 times 1, 1, 0. Vector v2, which is 1 divided by the root of 3 times 1 minus 1, 1. And v3, which is 1 divided by the root of 6 minus 1, 1, 2. Solution. We use the formula that when we write any element as a linear combination of the vectors in an orthonormal basis, the corresponding coefficients coincide with the scalar product between our element W and the corresponding element in the O and B. So in order to answer the problem, we need to compute scalar products between our element W and the vectors v1, v2, and v3. So here is a computation. The scalar product between W and v1 is equal to 1 divided by root of 2, and then 1 times 1 plus 1 times 1 plus 0 times 1. And this is 2 divided by the square root of 2, which is square root of 2. The scalar product between W and V2 is similarly computed as 1 divided by the root of 3, 1 times 1 plus 1 times minus 1 plus 1 times 1. So 1 minus 1 is 0. What remains here in the bracket is just 1, so we get 1 divided by the root of 3. And the third scalar product between W and V3 is equal to 1 divided by the root of 6 times 1 times minus 1 plus 1 times 1 plus 1 times 2. So here 1 and minus 1 cancel, and we get 2 divided by the root of 6, which is the root of 2/3. The answer is that the coordinates of W with respect to our O and B, v1, v2, v3, is root of 2, 1 divided by the root of 3, and then root of 2 divided by 3. Problem 5. Let E be the Euclidean space of all polynomials of degree at most 2 with respect to the scalar product, given as follows. The scalar product between f and g is the integral from 0 to 1 fx gx dx. Determine some basis in the orthogonal complement of the element 1. So we have seen in the previous problems, this is the same thing as the orthogonal complement to the linear span of 1. Solution. So we want to determine which polynomials belong to the orthogonal complement of 1. In other words, which polynomials are orthogonal to 1. So we will search for such polynomials in the general form a plus bx plus cx squared. And this polynomial is orthogonal to 1 if and only if the scalar product between 1 and this polynomial is 0. So here is the formula for the scalar product. So we plug 1 and a plus bx plus cx squared into this formula. So the scalar product between 1 and a plus bx plus cx squared is equal to the integral from 0 to 1 a plus bx plus cx squared dx. So this is equal to the evaluation at x is equal to 1. So because at x is equal to 0, we will just get 0 everywhere, of the following function: ax plus b divided by 2 x squared plus c divided by 3 x cubed. So if we evaluate this at x is equal to 1, we will get a plus b divided by 2 plus c divided by 3. So a polynomial a plus bx plus cx squared belongs to the orthogonal complement of 1 if and only if the expression a plus b divided by 2 plus c divided by 3 is equal to 0. So now we need to solve the linear equation a plus b divided by 2 plus c divided by 3 is equal to 0. Here we can take a as a dependent variable and b and c as free variables, and rewrite this equation as a is equal to minus 1/2 b minus 1/3 c. And for the free variables, we have the trivial equations: b is equal to b, c is equal to c. Now we can rewrite this in the vector form. The vector abc is equal to b times the vector minus 1/2, 1, 0, the coefficients at b here, plus c times the vector minus 1/3, 0, 1, the coefficients at c. So these two vectors, minus 1/2, 1, 0, and minus 1/3, 0, 1, will form a basis in the space of all solutions to our linear equation. In order to get a basis in the subspace which this linear equation defines, we should now interpret these vectors as polynomials. So these vectors give the coordinates of the basis polynomials in the standard basis. So the first vector corresponds to the polynomial minus 1/2 plus x. and the second vector corresponds to the polynomial minus 1/3 plus x squared. So these two polynomials form a basis in the orthogonal complement to the polynomial 1. And this completes the solution of problem 5. Problem 6. The inner product on R3 is defined such that the following vectors form an orthonormal basis. The vector v1, which is 1, 1, minus 1, the vector v2, which is 1, minus 1, 1, and the vector v3, which is minus 1, 1, 1. Determine the inner product between EI and EJ, where EI and EJ are the standard basis elements in R3. So please be careful here. This inner product, which is defined on R3, is not the standard inner product. So this inner product is explicitly described by the property that v1, v2, and v3 form an orthonormal basis. So when we now have to compute the inner product between EI and EJ, we compute this new inner product, not the standard inner product on R3. So in order to be able to determine this inner product between EI and EJ, we need to express these elements as linear combinations of the elements of our orthonormal basis V. So in order to solve the problem, we need to express all standard basis elements as linear combinations of elements in the basis V. We know how to do this. For this, we write the elements in the basis V as columns, then we write the vertical line, then we write E1, E2, and E3 as columns. This forms the identity matrix. And then we reduce the obtained 3 times 6 matrix to a row echelon form using Gauss elimination. So the row echelon form for this matrix will have the identity on the left-hand side. So here is the computation. And this is our matrix. If we read it column-wise, it will be 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we can use this one to kill everything else in the first column. So we subtract row 1 from row 2, and we add row 1 to row 3. Row 1 remains the same. Row 2 becomes 1 minus 1 is 0. Minus 1 minus 1 is minus 2. 1 minus minus 1 is 2. 0 minus 1 is minus 1. 1 minus 0 is 1. 0 minus 0 is 0. And row 3 becomes 1 plus minus 1 is 0. 1 plus 1 is 2. Minus 1 plus 1 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. So now we can swap row 3 and row 2, and row 1 remains the same, row 3 becomes row 2, and row 2 becomes row 3. And now we can use this 2 in row 2 to kill this minus 2 in row 3. So we add row 2 to row 3. Row 1 remains the same, row 2 remains the same. Row 3 becomes 0 plus 0 is 0. 2 plus minus 2 is 0. 0 plus 2 is 2. 1 plus minus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 1. So now here we have 2 and 2 on the diagonal. We need to make them 1. For this, we divide row 2 and row 3 by 2. So row 1 remains the same. Row 2 becomes 0, 1, 0, 1 half, 0, 1 half. And row 3 becomes 0, 0, 1, 0, 1 half, 1 half. And it remains to simultaneously add row 3 to row 1 and subtract row 2 from row 1. Rows 2 and 3 remain the same, and row 1 becomes 1 minus 0 plus 0 is 1. 1 minus 1 plus 0 is 0. Minus 1 minus 0 plus 1 is 0. 1 minus 1 half plus 0 is 1 half. 0 minus 0 plus 1 half is 1 half. 0 minus 1 half plus 1 half is 0. So now we have here on the left-hand side the identity matrix. which means that the matrix here consists of the coefficients of the standard basis elements in the bases v1, v2, v3. In other words, E1 is equal to 1/2 v1 plus 1/2 v2, E2 is equal to 1/2 v1 plus 1/2 v3, and E3 is equal to 1/2 v2 plus 1/2 v3. Now we can use the following property. So if we have two elements x and y, which are written as linear combinations of elements in an orthonormal basis, then the scalar product between x and y is just the sum of products of the corresponding coefficients. So we have the expressions for E1, E2, and E3, so we can compute. The scalar product between E1 and E1 is equal to 1/2 times 1/2 plus 1/2 times 1/2 plus 0 times 0. So this is 1/2. The scalar product between E1 and E2 is equal to 1/2 times 1/2 plus 1/2 times 0 plus 0 times 1/2. This is equal to 1/4. And of course, the scalar product is symmetric, so this is equal to the scalar product between E2 and E1. Next, the scalar product between E1 and E3, which is also equal to the scalar product between E3 and E1. So this is equal to 1/2 times 0 plus 1/2 times 1/2 plus 0 times 1/2. This is 1 divided by 4. The scalar product between E2 and E2 is 1/2 squared plus 0 squared plus 1/2 squared. This is 1 divided by 2. The scalar product between E2 and E3 is equal to the scalar product between E3 and E2 and is equal to 1/2 times 0 plus 0 times 1/2 plus 1/2 times 1/2. This is 1 divided by 4. And finally, the scalar product between E3 and itself is 0 squared plus 1/2 squared plus 1/2 squared, which is 1/2. This completes problem 6. Problem 7. Determine whether the following two vectors, the vector v1, which is 1 divided by root of 3, 1 minus 1, 1, and v2, which is 1 divided by the root of 2, 0, 1, 1. So determine whether these two vectors form an orthonormal basis in the subspace U of E3, which consists of all solutions to the linear equation 2x1 plus x2 minus x3 is equal to 0. Solution. First, let us note that the dimension of U is 2. So U is a subspace of the three-dimensional space E3, which is determined by one non-zero equation. So it has dimensions 3 minus 1, which is 2. And we have two candidate vectors, so far, so good. This has a chance. Next, let us check that our vectors belong to U. So the first vector is 1 divided by root of 3, 1 minus 1, 1. If we plug in coordinates in the equation, we will get 2 times 1 divided by the root of 3, minus 1 divided by the root of 3, minus 1 divided by the root of 3. This is equal to 0. So v1 belongs to U. Similarly, let us plug in the coordinates of v2 into the equation. So 2 times 0 plus 1 divided by the root of 2 minus 1 divided by the root of 2. This is 0. So v2 also belongs to U. So both these vectors indeed belong to U. Also, directly from the expressions of these vectors, we see that they're not proportional. So none of these vectors is a scalar multiple of the other one. In other words, they're not proportional, so they are linearly independent. Two linearly independent vectors in a two-dimensional space, they form a basis. So this, we have now checked these two vectors form a basis in U. So now we need to check whether this basis is orthonormal. So let's compute their scalar products with themselves. The scalar product between v1 and v1 is 1 divided by root of 3 squared plus minus 1 divided by root of 3 squared plus 1 divided by root of 3 squared. So 1/3 plus 1/3 plus 1/3 is 1. looking good. The scalar product of V2 with itself is 0 squared plus 1 divided by root of 2 squared plus 1 divided by root of 2 squared. Again, this is 1/2 plus 1/2, which is 1. Very good. And finally, the scalar product between V1 and V2. This is 1 divided by root of 3 times 0 plus minus 1 divided by root of 3 times 1 divided by root of 2 plus 1 divided by root of 3 times 1 divided by root of 2. So this is 0, and these two summands cancel each other. This is equal to 0. So both vectors have lengths 1, and they are orthogonal. So we can conclude that they form an ONB in our subspace U. And this completes problem 7. Problem 8. Determine an orthonormal basis in the subspace U of E4 generated by the following vectors. The vector V1, which is 2, 1, 1, 1. The vector V2, which is 2, 2, 0, 3. The vector V3, which is 0, 1, minus 1, 2. And the vector V4, which is 1, 0, 0, 1. Solution. This is a typical problem where one has to use Gram-Schmidt's method. But before we can use Gram-Schmidt method, we need to start from a basis in our subspace U. The problem only says that U is generated by these four vectors. There is no guarantee that they are linearly independent. So we need first to check which of these four vectors are linearly independent and thus form a basis of U. So we need to write these vectors as columns in the matrix and reduce this matrix to a row echelon form using Gauss elimination. A little hint, if one uses Gram-Schmidt method, it is very good if the vectors which one work with are as small as possible. So it's a good idea to write these vectors in a matrix not in the natural order V1, V2, V3, V4 as they are given in the formulation, but in the order where we write shorter vectors first. So we start with V4, this is apparently the shortest vector, and then probably V3, V1, and only then V2. So here is our matrix, V4, 1, 0, 0, 1 as the first column, V3, 0, 1, minus 1, 2 as the second column, V1, 2, 1, 1, 1 as the third column, and then V2, 2, 2, 0, 3 as the last column. So we need to do Gauss elimination, so we use 1 here to kill this 1. So we subtract row 1 from row 4. Rows 1, 2, and 3 remain the same. Row 4 becomes 1 minus 1 is 0, 2 minus 0 is 2, 1 minus 2 is minus 1, 3 minus 2 is 1. Now we have here 1 in the position 2, 2. We can use it to kill all other non-zero elements in the second column. So we add row 2 to row 3, and we subtract twice row 2 from row 4. Rows 1 and 2 remain the same. Row 3 becomes 0 plus 0 is 0, minus 1 plus 1 is 0, 1 plus 1 is 2, 0 plus 2 is 2. And row 4 becomes 0 minus 0 is 0, 2 minus 2 is 0, minus 1 minus 2 is minus 3, 1 minus 4 is minus 3. And now we see that the last two rows are linearly dependent. So we can just delete one of them. So we delete row 4 to get the following matrix: 1, 0, 2, 2, 0, 1, 1, 2, 0, 0, 2, 2. So this is almost a row echelon form. And we have here the leading elements in columns 1, 2, and 3. So the corresponding vectors, which correspond to these three columns, form a basis in our subspace U. Recall that column 1 corresponded to the vector V4, column 2 to the vector V3, and column 3 to the vector V1. So this is our collection of linearly independent vectors to which we will apply Gram-Schmidt's process. So let's do Gram-Schmidt. So the first ONB vector W1 is just the normalization of the first basis vector. In our list, it's a vector V4. So V4 divided by the length of V4, the vector v4 is 1, 0, 0, 1, and then the scalar is 1 divided by the root of 1 squared plus 0 squared plus 0 squared plus 1 squared. So this is 1 divided by the root of 2, 1, 0, 0, 1. This is the first vector in our ONB. To determine the second vector, first we determine an auxiliary vector w2 tilde. So this is defined as v3, so this is our second vector in the basis, minus the multiple of w1 with the coefficient v3 scalar product with w1. So since w1 is v4 divided by the length of v4, we can rewrite this expression as v3 minus v4 with the coefficient, the following fraction. The numerator is a scalar product between v3 and v4, and the denominator is a scalar product between v4 and v4, which we already computed, it's 2. So here is what we get. v3 is the vector 0, 1, minus 1, 2, minus the scalar product between v3 and v4. So v4 is a vector 1, 0, 0, 1. The scalar product is 0, 0, 0, 2. 2 divided by 2 from here. So it's just v3 minus v4. And the outcome is 0 minus 1 is minus 1, 1 minus 0 is 1, minus 1 minus 0 is minus 1, 2 minus 1 is 1. So w2 tilde is a vector minus 1, 1, minus 1, 1. And the second vector in our ONB, w2, is the normalization of w2 tilde. So we take w2 tilde and divide by its length. So the length of this vector is the square root of minus 1 squared plus 1 squared plus minus 1 squared plus 1 squared, which is the square root of 4, which is 2. So the answer is 1/2 of minus 1, 1, minus 1, 1. This is the second vector in our ONB. Let's continue to the third vector. First, the auxiliary vector w3 tilde, which is defined as the third vector of our basis, which is v1, minus w1 with the coefficient, the scalar product between v1 and w1, minus w2 with the coefficient, the scalar product between v1 and w2. So since w1 was v4 divided by the length of v4 and w2 was w2 tilde divided by its length, we can rewrite this as v1 minus v4 with the coefficient scalar product between v1 and v4 divided by the scalar product between v4 and v4. And then minus w2 tilde with the coefficient, the scalar product between v1 and w2 tilde divided by the scalar product between w2 tilde and itself. So v1 is 2, 1, 1, 1. v4 was 1, 0, 1, 0. The scalar product between them is 2 plus 0 plus 0 plus 1, which is 3. And the denominator is 2. We know that v4 is 2. Then minus the w2 tilde was minus 1, 1, minus 1, 1. The scalar product is minus 2 plus 1 minus 1 plus 1. This is minus 1 here. And w2 had length 2. So in the denominator we have 4. So this is the expression which we need to compute. And when we compute it, we will get 1 divided by 4 times 1, 5, 3, minus 1. To simplify our life, we can ignore this 1 divided by 4 coefficient and denote this vector 1, 5, 3, minus 1 by w3 two tildes. And w3 is just a normalization of w3 two tildes, so we should take this vector and divide by its length. So we have the vector 1, 5, 3, minus 1. Its length is a square root of 1 squared plus 5 squared plus 3 squared plus minus 1 squared. So this is 25 plus 9 plus 1 plus 1. This is the square root of 36, which is 6. So the third vector w3 is the vector 1 divided by 6 times 1, 5, 3, minus 1. And the answer is that the vectors w1, w2, and w3 form an ONB in our subspace U. Problem 9. Let E be the Euclidean space of all polynomials of degree at most 2 with respect to the scalar product where the scalar product of two polynomials f and g is the integral from 0 to 2 f times g dx. Let U be the subspace of E spanned by the polynomials 1 plus x and x minus x squared. Find some non-zero element in U that is orthogonal to the polynomial 1 plus x squared. Solution. So, by definition, any element in U is a linear combination of 1 plus x and x minus x squared. So let us look for an element orthogonal to 1 plus x squared in the form a times 1 plus x plus b times x minus x squared. We need to satisfy the condition that this element should be orthogonal to 1 plus x squared. In other words, the scalar product between 1 plus x squared and this element a times 1 plus x plus b times x minus x squared, this scalar product should be 0. And we can compute the scalar product using the formula which is given in the formulation of the problem. So we need 0 to be equal to the integral from 0 to 2 of the product 1 plus x squared times a times 1 plus x plus b times x minus x squared dx. So let us compute this integral. So this integral, first we simply multiply everything under the integral sign. So it's an integral from 0 to 2 of the following expression: a plus bx plus a minus bx squared plus a plus bx cubed plus minus b times x to the power 4 dx. So since one of the ends of the integral is 0, this integral is equal to the evaluation at x is equal to 2 of the following function. So we take the primitive function for this: ax plus a plus b divided by 2x squared plus a minus b divided by 3x cubed plus a plus b divided by 4x to the power 4 minus b divided by 5x to the power 5. So we plug in x is equal to 2 and we get 2a plus 2a plus b plus 8a minus b divided by 3 plus 4a plus b minus 32b divided by 5. So now if we compute this expression, we will get 32 divided by 3a minus 46 divided by 15b. And we need to solve this equation that this expression is equal to 0. One possible solution to this equation is a is equal to 138 and b is equal to 480. So a is equal to 3 times 46, which is 138, and b is equal to 32 times 15, which is 480. And so the answer, if you now plug in this a and b in our expression for the polynomial, so 138 times 1 plus x plus 480 times x minus x squared, which is a polynomial 138 plus 618x minus 480x squared. So this is a polynomial which belongs to the linear span of 1 plus x and x minus x squared, and this polynomial is orthogonal to 1 plus x squared. And this completes problem 9. Here are some additional problems and questions. Question 1. Prove that the scalar product between x and y is equal to 1/2 of the expression the length of x squared plus the length of y squared minus the length of x minus y squared. Question 2. Determine a basis in the orthogonal complement to the polynomial x for the Euclidean space of all polynomials of degree at most 2 with respect to the scalar product given by the integral between 0 and 2, the product of polynomials dx. Question 3. Assume that we are given a scalar product in Rx2 for which 1 plus x plus x squared, and 1 plus 2x plus 3x squared form an orthonormal basis. Compute the scalar product between the polynomial 1 minus x and the polynomial x squared minus x. Question 4. Find an ONB in the Euclidean space of all polynomials of degree 2 with respect to the scalar product, the integral between minus 1 and 2, the product of polynomials dx. And finally, question 5. Find some non-zero element which is orthogonal to the element 1 to 3 in the subspace of the standard Euclidean space E3, which consists of all solutions to the equation x1 plus x2 minus x3 is equal to 0. Thank you very much and see you next time.